Everyone, welcome back to Educate. Today we are going to continue with physical chemistry of all systems. So, uh, I see module one. Module one is matter. Module one, chapter one with Equilibria. The Equilibria have how many total power? Four topics. First Equilibria, acid base Equilibria, chemical Equilibria, and redox. So, we're going to start with topic one. The one which is physical. So, we talk about physically, but what you hear, what the face, what is the face? You know, start face.
Yes.
A face is simply a homogeneous and physically superous. Homogeneous, physically synchronous. But a system is better of common needs. That's a conclusion. A component is actually a chemical entity definite composition, which is different from other parts. Okay, let's consider a system. A system made up of water, water, ice, and steam. In this case, we're having a system made up of water, ice, and steam. Then in this case now, we wish to know the number of components or the number of phases. The phases are a bit is the homogeneous and physically distinct parts. So in this case, let's know the number of phases. So the number of phases are in this case we're having three phases. Water, which is a solid state, solid. Water means the liquid state, the bubble. Ice, which is the swim state, and steam, which is the gaseous state. So in this case, we're looking at the physical states of matter and the system. So we have three physical states. We have water, normal water, which is the liquid, ice, which is the solid, and steam, which is the gaseous state. In this case, we're having three phases. So let's go to the number of components. Combi. So how do we know the component? Identify the chemical X for each of the substances. But don't forget that our system is made up of ice, water. The formula is H2O. Ice. The formula is CH2O. Steam. The formula is CH2. In this case, we're having a three phase. How many components? Number of components here to change. Still water. Even though it's water, ice, steam. So in this case, the number of components we have one component. So let's go to other typical example where we're going to identify the number of phases and the number of components. So example, identify the number of phases on components. Components before we systems and water. Ethanol, kerosene, Between Bentley, water, benzine and natural. Music, oxygen. On a fait water level. So, we wish to know the number of components and pieces in a mixture made up of ethanol and water. So, in this case, for having ethanol and water, we know that ethanol and water mix and form a homogeneous mixture. So, the chemical entity here that we have, so yes, is number one, number two, and number three. So, one, the number of phases component. So, given that ethanol and water mix and form a homogeneous mixture, homogeneous mixture means what? A uniform solution, such that you are unable to distinguish water from ethanol. But in this case, now the number of components between two, because we have two components. The number of phases is only one phase, which is the liquid phase. But this liquid phase is not any type of liquid phase. It's a uniform liquid phase, meaning when water ethanol mix, it's impossible to distinguish the two. So let's go to the next two. Kerosene and water. So let's say we mix kerosene and water. These two components does not mix. Water stay and bottom while kerosene float above water. In this case, it's a two component. Kerosene, water, two component. Number of phases. Kerosene and water do not mix. In this case, we are going to have two liquid phases. A liquid phase for water, a liquid phase of kerosene. Yes. Three. So let's start now commonly see. One, two, three, four. Four components. No, component four. So let's sing the number of it. Oh, in this case, there are number you can say four phases. Look, all of these are components of air. Your air is a mixture of gases. All the gases you mix together to form only one component, which is air. And the component air can be separated by fractional distillation. Meaning all these gases combine together to form air. So it is only one phase, which is a gaseous phase, and a gaseous phase is a homogeneous. So consider this video. System. So if you have a system that has acted in we have iodine less, iodine something, or bromine. Et bromine, ça c'est bromine, liquide, gas atteint l'équilibre. Bromine, bromine. So that's a direct reaction. If bromine is placed in the cylinder, so let's say what a cylinder. I'm a cylinder. Inside the cylinder, have bromine, liquid bromine. If you heat the liquid bromine, the liquid bromine change it to a vector. So now the liquid bromine will change it to a vector. Here we have vapor. So vapor bromine. At every room, the vapor bromine will exert a pressure on the liquid bromine because the bromine liquid and the bromine they are something. So the vapor on top of bromine will exert force, that's the weight, knowing that the pressure is the force per unit area. Because this vapor units the mass. You have the mass, and if you have the mass, you will surely have the force because force and So this force mean like this is exerting a pressure. The pressure is force by the area. So this pressure exerted by action boom on liquid is called level pressure. So the level pressure, this is a pressure exerted by a vapor on its own liquid when a system has attained equilibrium. So the vapor pressure is CP. The pressure existed exerted by a vapor on its own liquid when the system is in equilibrium. So the gaseous bloom exerts a force on a liquid bloom when the system is at equilibrium. And that force is characterized by pressure. The force is the pressure is the force to meet area. So this pressure exerted on the liquid is quite called acceleration with Weber free. So I find that this is pressure that mine is that on its only foot. Is okay. Now we're about to see the ideal gas solution or the ideal solution because in this case we can have two types of solution. We have ideal solution and non-ideal solution. So let's see ideal. Ideal solution and also ideal solution and also ideal solution and how to. I'm sure I state that for two miscible liquids that do not react, the partial pressure, partial top pressure of each component is the mole fraction of the component times the pure pressure per tumbling. What is standard? The mole fraction VI stands for pure pressure. So comes law. So yeah, that's the mark. Now sit it. So two basically degrees per minute react the pressure. Pressure vapor pressure of each. The partial vapor pressure of each component is directly proportional to mole constant equals constant temperature. So on the board or half, I did solution and house will. So what's to stay in house in phase? I also said that for two miscible liquids, that do not react. The partial blood pressure of each component is very proportional to its blood pressure that does not build. Mathematically, how stop can be given you pi plus eta d d theta I. S I stands for the mole friction, pi stands for liquid. So let's consider two ID. Let's consider two ID solutions. Let's consider two into A, B, and in that case, we have two mixtures containing A and B. The different mixtures or the different solutions or component, they have their own partial pressure. So the partial pressure of A is AC plus C ST times B theta. Okay. Similarly, EV is equals SB plus theta. Okay. But ST is 10T n theta. AG is AG blah B theta. Also, ST is SB is equals to 1. So I give you the mathematical expression. The partial pressure, if you have two components, if you have a mixture whether of two components, A and B. The components in this case are A and B. So we can calculate the partial pressure of A in a mixture because we have just a mixture of two components. So in A there's B, in B there's also A. What to know the partial pressure? That means partial pressure of A found in B. The partial pressure of B also for A. So we have our mathematical expression, the general mathematical expression. Pi equals S I times B theta. And but in this case, PA is equals to XT times P theta of P. BB equals XB times P theta of P. But XA is anything over N to. That means the number of moles of A divided by the total number of moles. So SB is the number of moles of B divided by the total number of moles. But let's not forget that N total is of N equals N. So we're going to take a typical example. And this is Luis. For you. As it is. Super guns. Oh, big canal. And okay, some girls. Need first detail is relevante. Yo paso acá. Ahí. Is rabasis. Yo paso acá. Big. Good. E. Bom patch. Allah. Ethanol. Non, ethanol. Vite. Pas simple que si. Totality. For a vote to have a decision, example, an ideal issue contain 2.4 grams of methanol and 4.6 grams of few further of methanol repeats. So let's move our data. We should have the mass of methanol first sorry, gram, mass of methanol costs 4.6 gram, iketa methanol methanol it's 810 million per this data determine that's no more than 50. Yes, so those are the data due to us in the questions. Rising mixture contain 2.4 grams of methanol, 4.6 grams of methanol. The pure failure of methanol is 810 kilopascal, and for ethanol is 450 kilopascal. Calculate the mode fraction of methanol and methanol. The partial pressure of methanol and ethanol. C. The total pressure. So I'm giving you 1 minute to go to the exercise and read the exercise and uh, get in contact with the exercise. So in 1 minute's time, I'm going to do the question of this example on that piece.